Okay, so what I want to do in this video is to give kind of a half angle formula that Hipparchus used. Okay, so in other words, what we want to do is we want to compute chord of alpha over 2 if we know what chord of alpha is. So that's our idea here, that's the goal here. We want some expression that relates chord alpha over 2 to chord alpha. And it's kind of a long formula, so let me just write it over here, and I'm going to try to write it as legibly as possible. But ultimately, the thing that I'm going to prove is the following. Chord alpha over 2 squared is equal to the following. It is equal to 2r times 1/2, and then it's going to be 2r minus chord of 180 minus alpha. So that's the claim. That's what I'm going to show. The book shows how you can the book shows the translation from this to like the modern half angle formula using sines and cosines, and it's a discussion prompt to actually show how you can do that. So given this, how you can get the sine and cosine. A couple of things to note. Obviously, the 2's there cancel, but the way the proof goes, this is going to be one thing and that's going to be another thing, and I'm going to show it in 2 different steps. So I have it up there just so it's clear what's going on, and it's not clear here. This is an alpha. This is chord 180 minus alpha. In the previous video, we showed how chord 180 minus alpha is related to chord 180, and so we have this here. Okay, so this is how the proof is going to go. I had to, this is like my 3rd or 4th time recording the video, and so I've erased a lot on the circle, but this is what we have. So I added a point D here. This center is O. OD bisects this angle. This whole angle here is alpha, and this angle there is alpha over 2. Okay, so the first step in the proof is I want to draw a line segment from A to D and make a couple of observations. I want to draw a line segment from A to D and make a couple of observations about that. Okay, so the first observation that I want to make is that if you look at this angle right here, this angle is alpha over 2, and this arc length that it kind of traces out is goes from B to D. This angle here, beginning at A, this angle here also traces out the same arc length. Now, there's this theorem that says if you have a point on the circumference of a circle, and that traces out the same arc length as this angle at the center, then the angle at the circumference is half of this angle. So this angle is alpha over 2, so it means that this angle is alpha over 4. The really important thing is that we have the same fact over here with D to C. So this angle here sweeps out the arc length D to C. And that's exactly what this angle does here. This is also alpha over 2, so this is going to be alpha over 4. And so in particular, these 2 angles are the same, even though my drawing is horrible and doesn't depict that. Now, I will say honestly, I would rather my drawing be a little more faithful to what's going on here. Often, but also oftentimes when you draw diagrams like this, it's a little bit better if they're not exactly right, because you don't want because we don't want to use the fact that the picture looks right to prove the thing that we want to prove. We want to use geometrical arguments to prove what we're trying to prove. That's a sort of straight edge and compass thing that you can do. The other thing that is true that I don't have a great argument for. So let's look at BD. So BD, I need to draw this, and DC, I need to draw that. So BD is chord alpha over 2, and DC is chord alpha over 2. So we want an expression for BD and DC. And that's one of the things that we're going for. Now, this is what I mentioned in one of the discussion posts. One thing that we're going to have to prove a little bit later on is the similarity of 2 triangles. In fact, I can't say it yet. There's some other points that I have to draw before I can tell you what those triangles are. But one thing that is going to be needed is that the angle ADC, so that is this angle right here, that's a right angle. Now I can show it's a right angle just by doing a bunch of like stuff with the this is alpha 4, this is alpha over 4, so we know what various angles are and stuff like that. But the book just says that these two triangles are similar, and I'll say more about that later. The challenging part for me is showing that angle ADC is a right angle. Again, I can do it, but I just think there might be a more straightforward argument, and I hope somebody in the discussion forums can either give a complicated argument like I did, or maybe there's a better argument that my brain is just kind of refusing to look at. Anyways, like something involving like alternating angles that is like an easier or something like that my brain just isn't going to. Anyways, we'll set a pin in that, and I'll say more about that later in the video. Now the next thing that I want to do is I want to pick a P. I want to pick a point E on this line right here, and I am picking the point so that AE, the line segment from A to E, has the same length as the line segment from A to B. So AE is equal to AB. Okay, but now look what's going to happen. If I look at the triangle AED, my claim is that it is congruent, that is, it has the same sides and angles to the triangle ABD. Now, why is that? So again, it's AED and ABD. So what I want to show is that that we know the side angle and side of both of these triangles. We know a side angle side of both of these triangles, and if you know side angle side, then you know the two triangles are congruent. So for the AED triangle, I know this length AE, I know this length alpha over 4, and I know this length going from A to D. Okay, now for the triangle ADB or ABD, whichever way you want to look at it, we've got AD, alpha over 4, and AB. So remember, AB and AE are equal to each other. That's why AE is picked. So AE and AB, they have the same side. This angle is the same, and then this side right here, AD, it's literally the actual same side for both of them. So then what it tells us is triangle ABD is congruent to triangle AED. Okay, and a consequence of that is that this bottom piece, DE, has to equal BD, because the leg AE is equal to the leg AB, and then this leg AD is shared between them, so the third side on both triangles is BD and DE, respectively, and so they have to be equal to each other. So we know that that BD is equal to DE. We know that BD is equal to DE. Okay, but notice that BD, that's chord alpha over 2. DC, that's chord alpha over 2. So BD is equal to DC. Okay, that's going to be helpful in just a moment. Okay, so keep that in mind. Okay, now next step is to pick a point between E and C, call it F, such that that is a right angle. Okay, so now notice what we have here. DE, even though my drawing is horrible, DE and DC are equal to each other. Okay, so this triangle DCE, that is an isosceles triangle, and then this right here is a right angle. And so this point here bisects this line segment. In other words, the distance from C to F is equal to the distance from F to E, or equivalently, the distance from C to F is equal to 1/2 the distance from C to E. Okay, so CF is equal to 1/2 CE. CF is equal to 1/2 CE. Okay, so what does that do for us? Well, CE is this distance here. It's equal to AC minus AE. So this is 1/2 AC minus AE. Okay, I'm not going to rewrite everything, but remember that AE is equal to AB. So this is just AB. Okay, well, what is AC? Remember, AC is the diameter. So AC is just equal to 2R. So this is equal to 2R. And what is AB? Well, AB is chord 180 minus alpha. AB is chord 180 minus alpha. So this is chord Okay, so if you look at this part right here, this is this part of the formula. Okay, 1/2 2r minus chord 180 minus alpha. Okay, so that's C. This right here is equal to CF. Okay, so now here's where we're going to use this fact about the triangles. The claim is that triangle. The claim is that triangle ACD, ADC, triangle ADC is similar to triangle DCF. Triangle ACD is similar to triangle DCF. Triangle ACD is similar to triangle DCF. Now remember what it means for two triangles to be similar. It means all of their angles are equal to each other. So if you know that two angles of a triangle are equal to each other, you have two triangles, and you know two of the angles are equal to each other, then the third one also has to be equal because the angles add up to 180 degrees. Okay, so if you look at triangle ADC, okay, so and compare it to triangle CDF, well, if you look at ACD, and DCF, they share this angle right here. If the angle ADC is right, then that's a right triangle. So they have one common angle that they share. It's the same angle. There's a right angle that they share, so the other angle has to be the same as well. Okay, so given that angle ADC is a right angle, which again, I can give an argument for it, but it's a little more tedious than I would want. These two triangles are similar. So what this means is that AC, and they share a leg here. DC is a leg shared by both of them. Okay, so what it tells us then is AC over CD is equal to CD over CF. Again, that's by similarity. So now if we multiply both sides by CF and multiply both sides by CD, we get CD squared is equal to AC times CF. Now, this right here is CF, okay? This expression right here is CF. But notice what AC is. AC is just equal to 2R. So this is 2R times CF. So what I've shown is that CD squared is equal to 2R times CF. But what is CD? CD is exactly chord alpha over 2. So CD squared, which is chord alpha over 2 squared, is equal to 2R times CF. This is 2R, and then that expression there is CF by what I did over there. Okay, so this gives a sort of half-angle formula. Okay, what can we do with a half-angle formula? Because we want to be able to, we want to be able to say, okay, we've given a few different, ways that chord alpha is related to, chords of other things that you can do with alpha. We have chord alpha over 2 related to chord 180 minus alpha, and we saw how chord 180 minus alpha is related to chord alpha. Well, again, we want to have numerical answers for these chords, and so unless we can actually compute a chord of something, then kind of this is nice, but it doesn't practically solve what we're trying to solve. Okay, so let's think about this. Let's see if we can compute chord 60. Or the reason I said 60 is because I know that we can compute chord 60. But let's see, is there an angle that we can compute the chord of? I'm going to erase all of this now. Okay. So again, this is roughly the center. Should not have erased that. And let me just do something here. Okay, this right here is roughly 60 degrees. Okay, and so then if you look at something like that, this is what we're going to have. Okay, so what can we tell about this? What can we do? So chord 60 is equal to this right here. Now what do we know? We know this has radius r. Or this is the radius, so it has length r. We know this has length r. So we've got length r, and 60. Okay. So therefore we know this is an equilateral triangle. We know that this is an equilateral triangle, and therefore this has to be equal to r as well. So we can compute chord of 60. Using this half angle formula, this means we can compute chord of 30. This means we can compute chord of 15 and chord of 7.5, and so on and so forth. All right, so using these two formulas, or I guess maybe three formulas now, the chord 60, chord alpha over 2 formula, and this formula for chord 180 minus alpha in terms of chord alpha, we can now compute all of the angles from 0, or the chords of all the angles from 0 to 60 at least in increments of 7.5 degrees. Okay, and then we'll see how maybe either in the discussion or in an upcoming video how we can compute more angles from those as well.